Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from 6.1 and 6.2. So, when we're looking at these problems, the first thing we're thinking about is you probably have seen, something like the square root symbol and the square root of 25, and most people know that that's 5. But I think what we need to do is kind of break that down a little bit more, just to kind of get a better understanding of what is going on there. Let's scroll down here. I can do that a little quicker this way. Let's scroll down here to some of these rules. I think the best one to take a look at is right here. So this is called the principal nth root of a number. So it's symbolized by the nth root of a, where n, just reading right off of here, the nth root of a, where n is greater than or equal to 2, is an integer. So this is called the root index. N is called the root index. And that, let's see. Once again, that's an integer that n is greater than or equal to 2 and is defined by this following statement. It says the nth root of a, let me zoom in a little bit. It says the nth root of a equals b, which means that a equals b to the nth. So there's a real connection going on there. Let's take a look if we could kind of walk through some examples with some numbers. So if I start off, let's say, and so my root index, let's just make it a 2. And whenever the root index is 2, we don't put anything there. It's just assumed. That's why if you did see something like the square root of 25, you didn't have to put a little 2 for the root index of 2. It's the most common, so we don't put anything there. But anyhow, when we see something like this with a root index of 2, we know that that equals, well, maybe we should take a second and realize that doesn't 25 equal 5 times 5? And another way to think about it is 5 squared. And so really what I want you to start realizing is that when the power of this base number is the same as the root index, well, they are inverses of each other, and we'll basically simplify it down to just 5. Okay. So now if we follow along with this, basically it's saying, well, if you start with 25 and take the square root of 25, you will get 5, right? But if you go the other way and we start with 5 and we square it, right, you end up getting, whoops, I'm used to going over there. I've got this shortcut. You end up getting 5 times 5 is 25. And so you can really see this inverse type of thing happening here. Another little idea is, we call this the square root. And it probably came from the idea of looking at the sides of a square. So like if I was a guy who builds squares and I want to build you a perfect square that has an area of 36. Well, if I know this little tool right here, square root, right? The square root of 36, well, 36 is actually a perfect square, 6 squared, right? 6 times 6. And like I said, I want you to get used to the idea that when the root index is 2 and the power is 2, well, out comes that base number of 6. Now, what was that good for? Well, if I'm a square maker, that tells me that I need to make a perfect square that has one dimension of 6 and the other dimension of 6, and I will have a perfect square with an area of 36. So this actually finds the side of a perfect square. You can kind of think of it that way as well. But we kind of have to expand our ideas a little bit more, meaning notice the value up here in our rule has an n, so that is a variable. That means it can be different things. So for instance, what if we had the nth root, I'm used to using that, nth root of 8. Now let's not make it the nth root, let's make it something, right? Why don't we make it a 3? So now we have the cube root of 3. Now this tells us we're not looking for perfect squares, we're looking for perfect cubes. And I picked 8 for a reason because 8 is a perfect cube. And you can go over here and kind of break down 8 and realize that 8 is 2 times 4, and 4 is 2 times 2. So wow, 8 is a perfect cube, right? 2 times 2 times 2, or 2 cubed. So I can rewrite this as 2 cubed, and I'm going to change my colors. So I'm looking for the cube root of 2 cubed. Well, once again, that cube and the cube root match, and when that matches, what happens? Well, what happens is it will simplify down to 2. Just like we did with the square root of 25, right? 5 squared, the squares match their inverse, so we take the inverse, which we basically just take the 2 out, okay? So if you kind of think of it in this way, you can continue to break down not just square roots, but nth roots. So I'm going to say 16. In this case, I'm going to make this nth root. I'm going to make it the 4th root. Whoops, that's a little bit small. Make the 4th root. So basically, I'm looking for 4 of the same numbers, and yes, you could in fact realize that 16 is what? 2. Whoops, that didn't work. 16 is 2 times 2 times 2 is 8 times 2 is 16. And of course you could write it that way. Now we have to make sure if the root index is not 2, we must show our index. And then that would just say, well, I need 4 of the same number, right? That's what a 4th root is looking for a perfect 4th power. But really, just for purposes of just seeing this pattern as you go in algebra, it's really better to write this as 2 to the 4th power, and you can identify that power matches the root. And when that power and the root match each other, out comes this little 2. Okay, so we're kind of getting that idea now. Now the thing we did not tackle yet would be these 2 bullet points. It says if n is greater than or equal to 2 and even, then a and b must be greater than or equal to 0. If n is greater than or equal to 3 and odd, then a and b can be any real number. Okay, so we're going to get into that a little bit more. Let's just show an example that I think most people have seen from beginning algebra. And let's see, it says if n is greater than or equal to 2 and even, then a and b must be greater than or equal to 0. Okay. So let's see what happens here. Let's take this first case where we'll take a root index of 2, so it's even. Notice that that's even. And what happens if we take a negative number like negative 16? And you can really see this dilemma here, because when I'm trying to simplify a square root, I'm looking for 2 of the same exact numbers being multiplied, so it's a perfect square. And if I have a perfect square, it gets simplified by a square root, it's inverse. Now the real problem here is to make a negative 16 inside the square root. To make a negative, right, one number has to be negative and the other has to be positive. And because one has to be negative, one has to be positive, these are not perfect squares because they're different numbers. So whenever we have the square root or even more general, an even root index of a negative number, this is actually going to be considered not a real number. It actually is a number, and in this class, towards the end, we actually figure out what that is. So we don't want to say it's not defined. It actually is a number. It's just not a real number, and it is something we define later on. Now I want to get into this business of absolute values, and this is something that this book just kind of gives you a little taste of and then backs off on most of the problems. So it's good to know about this, but they really don't ask it much. You have to be careful on the wording, and I will definitely highlight how this book asked the question. But this absolute value is, here's what it says. If it says if the nth root is greater than or equal to 2 is a positive integer and a is a real number, then so remember how I was saying when the power matches the root index, out comes what? Out comes a. Out comes that base. Why do we have to put an absolute value here? Well, so right now we're taking a look at this case right now. Go back to, let's call this case number 1. Let's use case number 1. Case number 1 is when the nth root is even. Okay, so let's take an even value. So let's take an even value, even nth root, so like let's say square root. And what I'm going to do is I'm going to make this a value. It says a is a real number. Remember, real numbers can be positive or negative. So let's make this a value a negative 16. Nope, I take that back. I'm already having regrets. Negative 4 squared. Now the difference between this and the last problem I did, okay, this was a negative 16, but it was not being squared, so this is definitely a negative number, and that does produce not a real number. So the difference here is it looks subtle, but it's a big difference. And usually because this is an actual number, what is negative 4 times negative 4? And you guys all yell out, negative 4 times negative 4 is positive 16. And what's the square root of positive 16? It's just 4. And so notice we started, let me highlight. We started with a negative 4. And when we took the square root of that, we ended up with a positive 4. Now, once again, why did it turn positive? It turned positive because of this little 2, right? Because when you multiply a negative times a negative, you're going to get a positive. And so, therefore, whenever the nth root is even, because an even is going to give us an even amount of negatives, will always turn positive. Therefore, what's going to happen is that even power, in this case 2, is going to make the negatives into a positive, which would give us a positive 4. Now, so you didn't need to use the absolute values like we have there, because it just kind of came out while we can see it, because we multiplied a negative times a negative. But the thing is if you have a variable here now, let's do the same problem, but instead of having a negative, I'm just going to have x squared. Now the problem with x squared is I don't know if x is positive or negative. So I have to be sure. Now look at, if we actually took this, if we actually did this problem up here that we just did right here, if we actually did it without the knowledge of this piece right here, notice how you would have done it. You would have had to say, well, my power of 2 matches my index, so I take out this base. And when you take the base out, you would have taken out negative 4. And that's why this problem is saying, whoa, wait a minute. You better absolute value that. And why would you absolute value it? Because there's 2 negatives inside here that became positive. So like I said, that kind of thing, we usually don't miss it when it's a number, because you can see a negative times a negative. But when it's an x value and you don't know if x is positive or negative, it's easy to miss it. So when you have a root index that is even, and we don't know if this x value is positive or negative, and we don't know because they say it's a real number, then whenever we simplify it, okay, we have a power of 2 and an index of 2. Well, therefore the x comes out, but we have to take the absolute value of it, because if this is negative, well, this would end up being positive because there's 2 negatives being multiplied. If it's positive, it's going to be positive as well. So we have to be careful whenever we're simplifying square roots, fourth roots, even root indexes when you have a variable there that we don't know if it's positive or negative, okay? So that's kind of a tricky little piece, right? It's a little bit tricky. Why is it that if we go to number 2, we don't have the absolute value? Well, number 2 is talking about what if the index is odd? Well, if the index is odd, that would be a cube root of something. So let's take the cube root of, let's say, -2 cubed. And we're saying, the formula is saying, well, when you have a power of 3 and an index of 3, out comes that base, which is just a -2. And we're saying in this case, don't take the absolute value because the answer is going to be a -2. And so you might say, well, why would that remain negative, right? Why doesn't that just become positive like it did on number 1? Well, when you really break down -2 cubed, -2 times -2 times -2 remains -8, right? And the cube root of -8 actually is just a -2. And you can see the reasons for it. -2 cubed is -8. And when you have an odd number of negatives, 3 of them in this case, it stays negative. Okay? In other words, a negative times a negative times a negative, right? A negative times a negative makes positive. A positive times a negative becomes negative. So an odd number of negatives being multiplied together will remain negative. Okay, and an even number of negatives being multiplied will become positive. Okay, so that's sort of something that kind of blows people's minds a little bit, and you have to kind of be aware of it. They tell us about this absolute value, and then they don't ask the question much, which is a little bit annoying. If you go into pre-calculus, they will make sure that you take the absolute value when you're simplifying. Let's see. I think I want to start doing some problems now. So let's go ahead and do that. Go back to the beginning, and I better zoom out. All right, so it says find the root. Well, we can see that this root index, I think I'm going to get rid of this over here. You can see that the root index is 3. I think I'm going to zoom in also. I'm going to need to make that pen tip a little smaller. The root index is 3. So really, the game here is if I could find a perfect cube, that will simplify out, right? Any perfect cubes in that number must simplify out. Now, if I take the number inside the radical, and by the way, just for language, I already told you that is called the root index. And this number inside here is called the radicand. It's just nice to know what they're called, so when I refer to them. So you take that radicand, and didn't need to zoom anymore. Take that radicand, and prime factoring it would work, but prime factoring can take a little bit longer, could take quite a bit longer. Let's go ahead. If you knew the fact that we're looking for perfect cubes, you have a calculator, actually take a perfect cube of it, but that's, let's see what's going on. So if I start factoring this down, 6 times 36 is 216, and 36 factors down to 6 times 6. Now someone might say, wait, 6 factors down to 2 times 3, and that is true, and that's something you actually could do, but you have something already pretty sweet happening here, and that is you already have a perfect cube, don't you? So really, you can rewrite this cube root, so the radicand 216 really is just 6 cubed. Now remember, we are looking for cube roots, not square roots. And when you're looking for cube roots, if you have a power of 3 and an index of 3, that's sweet. Out comes what? Out comes that base number of 6. So the cube root of 216 is just 6. Just to tackle that idea that I was just talking about, that someone sometimes asks in class, they might say, well, how did you know to stop at 6? Because I would have continued and factored it down to prime factorization, and we'd get different answers. And I'd say, nope, you wouldn't get different answers. You would get, so we started with 216, and that was a cube root. And we know cube roots, we're looking for perfect cubes, right? So, well, that's equal to what? What do we get? Well, we got 2 times 2 times 2, so we got 2 cubed. And we also end up getting 3 times 3 times 3, so we got 3 cubed. So, oh, and it's a cube root. So same thing happened anyhow, right? I've got the power of 3 and a cube root. Well, those are inverses, so out comes a 2. And I've got a power of 3 and a index of 3, so out comes a 3. And it just simplifies and it multiplies when it comes out, or you can really just think they're inverses of each other. So a power of 3 and an index of 3 are just inverses, just like square rooting and squaring. And we get 2 times 3 is 6, just like what we got back there. So it's faster if you can find the biggest perfect cube. Okay, so we got this to be 6. The answer is A. And then we move on to the next one. Now remember when we saw an index that happens to be odd? And odd indexes are just fine having a negative under the radical, right? And why is that? Because when I take this radicand, which was, let's just start with 343, and it's negative, it turns out I can factor this down to 7 times 49, and then 49 factors down to 7 times 7. Okay, now let's be careful here. This was a negative, and a negative times a negative times a negative is positive. Is negative still. So this negative 343 equals negative 7 in parentheses raised to the third power. Okay, so I can actually rewrite this as the cube root of negative 7 in parentheses raised to the third power. Okay, now once again, the power of 3 is matching with my index or indices of 3. So out comes that base of negative 7. And when we have odd indices, right, we don't take the absolute value of it, right? And so the answer is just negative 7. Okay, let's take a look at the next one. Next one is we're asked to simplify. Now the negative is on the outside, and if the negative is on the outside, it really doesn't affect anything. It affects something, right? It makes the whole answer negative in the end, but it doesn't affect us dealing with the radicand and the indices, okay? So that's kind of what I'm trying to say. I better be a little more clear on how I say that. It does affect the problem, right? But it doesn't affect our work inside the radical. So what we want to do is we see 124, 124. Let's see, did I write that anywhere? Not 124, I can't see right now. It is 1024. And 1024, actually, if we're looking at it, we can actually factor this down to, I think I'm going to grab a calculator on this. So this factors down to 16 times 64, or 64 times 16. And 16 factors down to 4 times 4. 64 is, what, 2 times or 4 times 16, or 16 times 4. And 16 is 2 times 2. Oh, where I got that. It's way too late right now. I'm making a lot of mistakes. 16 is 4 times 4. I'm going to bring this 4 down from the previous step. I'm going to bring this 4 down, and this was also a 4. It turns out that 1024 is 4 times 4 times 4 times 4 times 4, which is 4 to the 5th power. Now, the thing about this, let's see. I'm going to write it under. There's the negative. I've got this 5th root. And I now can write the radicand, which is 1024. I can now write the radicand as just 4 raised to the 5th power. So once again, this negative is just going to drop down. And now, when the power of 5 matches up with the identical index of 5, out comes this interior radicand base, and we get an answer of -4. So this one says simplify the given expression. Now there is a difference here. The difference is all these previous problems, the radicand happened to be a number, a number, a number, and a number. And with a number, we can visually see if it's positive or negative. On this particular problem, it is a variable, y. And I do not know if y is positive or negative. And it's not giving me any clues. A lot of times with many of these problems, it will say something like, all variables are positive, or all variables are non-negative, or something like that. And when it does that, it really saves us from having to use the absolute value from that property I told you about earlier. But in this case, it doesn't say this. So we have to. Now, the beauty of this thing here is we already can see that the power, y to the 10th, is matching beautifully with my index of 10. When that happens, these radical expressions will simplify really easy to make a y comes out. But because that index, because it's even, you must put an absolute value bar on that. Okay? Because if it was a negative y, think about this. If this was a negative y right here, and you raised it to the 10th power, let's say that was -2, you raised it to the 10th power, an even number of negatives is going to make it positive, so we want to make sure that stays true in this problem by using the absolute values. So this answer is, in fact, the absolute value y. Let's put a little hook on the bottom so we know it's a y for sure. And the next problem. Oh, we changed up a little bit, didn't we? We now have exponents that are not just integers. We have exponents that are rational or fractions. So write the expression as a radical and simplify. Well, we have to know how does this turn into a radical. So we have a rule for that somewhere. I did show you. Yeah, here we go. So here's the rule for that. It says, so this is the definition of a base raised to a fraction, or also known as a rational exponent. So let's just use some color and just kind of talk about it first. If you have a base of a raised to the m power over n, it's a fraction, m over n, the denominator is going to be your index. So the denominator actually tells you the indices or the index, and the numerator tells us the power a is raised to. Okay? Notice that m and n are not the same thing, so we're not just going to simplify out to something simple, but it does show us that we can start with a radical and write it as a rational exponent, or we can start with a rational exponent and write it as a radical. This equal signs allows us to go both ways. Now, what is this business over here? Well, this business over here is just saying you have your options. You can simplify it like this, option number 1, or you could simplify it like this, option number 2. And in this case, the denominator it's still the index. You have your a, your radicand that goes inside. But instead of raising a to the m power, we're going to raise the whole expression to the m power. And both of those, option 1 and 2, gives us the same answer. Option 2 actually ends up being easier to deal with as long as this stuff in here, simplifies easy, right? If that simplifies easy, it'd be easier to simplify it and then raise it to a power, because raising a to the mth power might make it more complicated and harder to simplify. Both answers would give you the same answer though. They both are equivalent. Let's take that. Actually, I want to do an extra little thing because over the years of teaching, when I show rational exponents, a lot of times it's people are just like, I can't get any picture of what's going on. When I say something like 5 to the second power, you would say that's 5 times 5, and so people have a good idea what that is, right? And also, we could even just say that using exponents like 5 to the second power is a way of condensing multiplication of 5, repeated multiplication of 5, right? I mean, that's one of the beautiful things of it is, if someone said, well, I have 7 times 7 times 7 times 7 times 7 times 7 times 7. Well, that sure takes a lot of space. How about if we call it 1, 2, 3, 4, 5, 6, 7? I didn't mean to make it 7 to the 7th power. But anyhow, you get the idea that exponent saves space. It's just repeated multiplication of that base. And it's handy that way. But when we've got this rational exponent, it's hard to conceptually see what the heck is going on. So I came up with this little example to try to show, and you could take it or leave it. I mean, you need to have this memorized to use. But let me show you this example that I think kind of sheds a little bit light on this. So we all agree that 16 to the first power, I'm going to write it in a funny way. 16 to the, I'm going to write it as a rational expression, and I already see that it's just too darn tight when I'm doing exponents, so let me try again. Make it a little bigger. 16 to the first power can be thought of as 16 to the 4 over 4 power. I wrote it as a fraction or a rational number, and we all know that 4 over 4 is the same as 1, so no one's going to tell me I'm lying here. Those two things are equal. And I'm going to take it even further than that. I know that 16 to the first power is just 16, so 16 to the 4 over 4 is just 16, which equals 2 times 2 times 2 times 2, right? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So that all equals. And so I want you to see that first of all. And so that doesn't seem like anything earth-shattering. Let me get you used to that idea. Now I want to write another thing. I want to write, well, what about 16 to the 3/4 power? Now that doesn't equal that. But let me go back a second here. Let me get another color just to be fun here. That's not that fun. But anyways, it says 4 out of 4. Now, how many factors do I have here? Well, I've got 1, 2, 3, 4. This one says I want to have 4 out of 4 of those factors. So I want to have 4 out of 4. So we're saying this equals 16, which we've been saying all along. So that seems like a waste of time. But I think this helps us right here, though. How about 16 to the 3/4? Well, it's saying I want 3 out of 4 of those factors. I want 3 out of 4. So what's 2 times 2 times 2? It's 8. Huh. Okay. Let's take this example right here and apply this new rule that we have up here. Okay, and let's see if we get 8. So this says 16 raised to the 3/4 power. According to the rule, if I change it to a radical, that's 16 inside. And what colors did I use? I read red for the numerator. So the numerator is 3. I usually start with the indices. The denominator is always the index, so I just put that right there. And then, now answer a question, is the 4th root of 16 an easy number? Yeah, it is. It's a 2. So I would prefer to cube it after the fact because it's just easier. If you cubed it inside here, you would get the same answer, but you would have to cube that number and then break it down. And that's a lot more work. So in this case, now remember we work from the inside out. So a big question here is what's the 4th root of 16? And we already know that 16 is 2 times 2 times 2 times 2. So this, in effect, if you want, we could rewrite that 16 as what? 2 to the 4th power. And we said when the power matches the index, out comes that little 2. Don't forget we still have this raised to the 3rd power. And that means 2 times 2 times 2, which is 8. Huh, okay. So my little representation of this fraction and doing it in this kind of funny way actually gave me the same exact answer as if I did it with this new way. I think this right here is a little more conceptual because we can kind of physically see what that's doing. And this is a rule that you're just going to want to know because you need to do it fast. And you can't always show every problem this way, right? Let's do it again using another 16. Let's say 16 to the 1/4 power. Let's try that. So if I had 16 raised to the 1/4 power, according to my funny way of doing it before, well, we know 16 is 2 times 2 times 2 times 2. And 1/4 says I want 1 out of the 4. That's just 2. So 16 to the 1/4 is 2. Okay, well, let's go ahead and do this again, but let's use our new found rule. Our new rule says I can rewrite this rational exponent rather, yeah, I said that right, into a radical expression, right? And the indices is the denominator, so it's a 4th root. And of course my radicand is the base 6, and I raise it to the 1st power, which I could put it inside or outside, but 1st power doesn't change anything, right? So I don't even really have to show that. Whoop. Okay, and what is the 4th root of 16? Well, remember 16 is 2 to the 4th power, and there it is, my power matching my index, so out comes the 2, which is the same answer we got up there. Okay, so we need to get it to this level so we can just use the rational exponent rule to write it as a radical and vice versa. So with that, let's go ahead and do some of these problems. If I can see where we're at. Okay. So, and the more you do of these things, the quicker they get. There's 16, right? 16 to the 1/2 power. It says, write the expression as a radical and simplify if possible. Well, radical is this guy. It's called a radical. We know by that little rule we did that the denominator is 2, so the index is 2. We know that the base of that exponent is 16, and the numerator is 1. So you could put a 1st power there or on the outside, but once again, raising something to the 1st power doesn't change it. And now what are we looking for? We're looking for trying to simplify this, okay? And can we rewrite 16 as a perfect square? Yeah. Isn't it 4 squared? So the power is 2 and the index is 2. That's a beautiful thing. That means that they inverse or they reverse each other, and we just get that base 4 inside. Okay. All right. Okay, what about this one? Why don't we rewrite this as a radical? So we've got 64 inside. Remember, our denominator is 3, so our indices is 3, and the power is 1, so we don't have to worry about that. Can 64 be written as a perfect cube? And this takes a little while to start recognizing these things, but you'll get better at it. And you could prime factor it down. It turns out that 64 will factor down to 4 cubed. So we've got 4 cubed. And there's that cube, power of 3, matching the index of 3. So of course what comes out is just that 4. Okay. All right. Now, something that I wish this book did a little more of, and I think I'm going to do it. I've got a little space here. I think I'm going to go down here. Something to realize here is that, like we said before, if you had, let's say, square root of negative, and I already did this, but the book doesn't seem to do as much, but the square root of negative, let's say, 64, well, we have an even index and a negative inside the radical. This is not a real number. Okay, and once again, to kind of verify that or get it to make sense in your head, I'm looking for a perfect square, which would be something times something, right? And in order to get a negative under the radical, one of them would have to be negative and one of them would have to be positive, and there's no way we can make them a perfect square. And so anyhow, this turns out to be not a real number. But what would happen if it was the cube root of a negative 64? And that actually works out okay because negative 64 is the same as negative 4 cubed. And so the answer would still be a negative 4. Once again, what made this not a real number with a negative under the radical was because the index was even. And why did it work here? Because the index was odd. And what's so great about odd indices? Well, odd indices, odd number of negatives is going to remain negative. Whereas a negative under the radical, when I I have to use 2 negatives, it's not going to stay negative. Okay. So the reason why I'm kind of bringing this up again is if we had this problem, I wanted to show you the difference between negative 16 to the 1/2, let's say, versus negative 16 in parentheses to the 1/2, right? Those almost look the same. I wanted to tackle that. Well, when you don't have parentheses and you're talking exponent, the exponent of 1/2 is only being applied to the 16. If they wanted it to be negative 16, we would write it this way to make sure we include the negative base as the exponent. So in this case, over here, number 1, the base is 16. It's not negative 16. Over here, the base is negative 16. So you see there is actually a big difference. So let's go ahead, because the negative is not included with that exponent, it's not included with our square root. Once again, the indices is the denominator, which is square root. And that base, which was not negative 16, it was just 16, goes inside the radical and it's positive. Okay, so now when we simplify, what's the square root of 16? Well, it's 4, and then we bring down our negative and we get a negative 4. Once again, why was that okay? Because the negative was on the outside. It was not included with the exponent, and it's not included inside the radical called the radicand. Now, this is very different over here. Let's call this versus option number 2. This is very different because the negative is part of the base, so it's included with the rooting when we go to radical. we go to the radical, and the radicand is negative 16. And once again, because the denominator is 2, we're looking for a perfect square, and there's no way we get a perfect square with a negative radicand. So this one is not a real number. Okay, so those are just little things I've seen over the years of people having little misconceptions. I kind of wanted to tackle that a little bit. So let's see if I can go back to where I was. I think it was somewhere there. Okay, so when we're taking a look at this, make that smaller. Once again, the radicand, right, the base is not negative. So that negative is not included when we turn this into a radical. Okay, so inside is just 625. Now we take a look. The denominator of the fraction was 4, so our indice or our index is 4. Once again, the negative is on the outside and it's not affecting inside. Once again, the index is 4. Did that switch? Yeah, it did switch. Huh, that's funny. Okay. So now the question is 625 a perfect fourth? Can I write that in the fourth power? And you can look a little bit, search a little bit, do some calculator work. You find out that 625 is 25 times 25, and 25 factors down to 5 times 5, and 5 times 5. So this is 5 to the fourth power. How perfect is that? So this is 5 to the fourth power, and when the power matches the index, out comes that base. Don't forget that there was a negative hanging on, and that's got to stay. Answer is negative 5. Question, some people might be asking, what would happen if there were parentheses around that whole base, meaning now the base is negative 625? Well, a negative base of 625 and an even index, right, is going to be not a real number. But because the parentheses were definitely not there in this problem, well, then the base wasn't negative, so we were fine. Next problem, evaluate. The base is now negative. Okay, let's go ahead and see if we can rewrite this as in radical form, negative 729. Looks like our denominator is 3, so our index is 3. Notice that the index is odd, so having an odd index and a negative radicand is okay. Question is, can I write this number as a power of 3, or a third power? And if you take 729, you will realize after messing around with it that 729 factors down to 9 times 8. 9 times 81 rather, and 81 is 9 times 9. So 729 will actually factor down to 9 cubed. I'm sorry, this was a negative 729, so a negative 9 cubed. And the fact that that's odd doesn't bug us. The answer is going to be negative 9. Okay, where are we at? Number 9. So number 9 is, it says, please rewrite the following radical. So it's already a radical with a rational exponent. They want us, from what we were doing, they want us to go backwards. They want us to get rid of the radical symbol and write it as a fractional exponent. So your first question would be, what is the radicand? The radicand is x over 2, and that's your base. Okay, now what is my exponent? What's the power? Well, remember, it will be a fraction, and the index of 8 will be your denominator. And the fact that I don't see the power there means it's to the first power if we have to put it in, but we really don't need to. And if it's to the first power, that means the numerator is 1. So we have a quotient of x over 2 raised to the 1/8 power, and that is the answer to the problem. Next problem, evaluate. Okay, we've got this problem right here. Let's see what we can do with this. It says evaluate the following expression if possible. And I don't know about you, but looking at 9 raised to the 3/2 power, I am not sure what to do with that at all, other than why don't I see if I can rewrite that into something more comfortable. The base of this rational exponent is 9, so that becomes your radicand inside. We also can see that the denominator is 2, so that is your index. And on this one, we have a power of 3. So we better do something with that, and we have two options. You could either put the power of 3 inside, which is going to make that 9 a very big number, so I don't feel like doing that. I might be forced to do that, but I want to try something else first. I would prefer to put the 3 after. And what's going to drive this decision? Well, what drives the decision for me is the question, is the square root of 9 something beautiful? Does that simplify down? And yes, it does. The square root of 9 is just 3. And so now I must continue with the problem. This says 3 to the 3rd power. And I know that 3 to the 3rd power is 3 times 3 times 3, which is 27. Done. Okay, number 11, it says evaluate the following expression. I've got a jacket on here and it's getting hot, so this math is hard work here. So anyhow, this says number 11, evaluate the following expression if possible. Once again, 25 to the 3/2 power is kind of hard to wrap my brain around, right? Conceptually, what the heck is that? But fortunately, we have the ability to write it as a radical. The base of this exponent is our radicand inside 25, and our denominator of 2 is my index, and my numerator of 3 is my power exponent. That is legal to put that there, but that's going to make it a very big number. And so the question I would have is the square root of 25 something nice? And yeah, it's really nice, right? Isn't it just 5? So if that's the case, then I would rather, why is that not working? I would rather raise it to the 3rd power after I made that nice and simple inside there. So let's do this now. So what did I say the stuff in purple was going to be? Well, the square root of 25 is just 5. And it says it better be raised to the 3rd power. And I know that this is just 5 times 5 times 5. 25 times 5, well, 125, right? So we've got this as 125. Whoa, thing's freaking out on me. 125. And so this is 125 as a final answer. And next problem. Evaluate the expression. Looks like a little bit of space to work down here. So in this case, because of the parentheses, this thing's having problems. Because of the parentheses, inside the radical, so when I change this to a radical form, inside the radical is going to be my radicand, which is the base, negative 1,331. Of course, my denominator is my index of 3. And my power in this case is 2, and I don't know if this is something beautiful inside or not. I'm going to start with this because that's valid. I want to see if that interior, which I'll do in purple, actually simplifies down to something nice. So what I need to do is I need to take 1,331 and start factoring that. And it turns out that's 11 times 121. And 121 is 11 times 11. So notice that interior is 11 cubed, which perfectly matches with my index cube, right? I'll just copy down the rest of the problem. But the beautiful thing is that interior right here, 11 cubed, so the power matches the index. Out comes the base of 11. Don't forget my power of 2. What's 11 times 11? That's just 121. And that is my answer, which goes right here. Wait a minute, sorry about that. I just fouled that up because I dropped my negative. It was negative, and it absolutely is fine because negative 11 raised to the third power is still negative 1,333. So having an odd index with a negative number is not a problem. So this will come out as a negative number. And then, see, look at that. I got the right answer even though I screwed it up. I hate that when that happens with students because it's just, anyways. Look at this. A negative 11 times a negative 11 still is 121. So at the end of the day, if this is multiple choice, the teacher, oh, yeah, he knows what he's doing, bingo. But really, I dropped my negative, but it fixed itself because the square, whatever. Sometimes you get lucky, huh? So anyways, let's take a look at the next problem, which is number 13. Now 13 is there's something new here. What is it? What is the new thing? The new thing is, I'm using blue. No, the new thing is a negative. Ugh. What about negative exponents? Well, now this looks like hectic right here, but let me start easy. Do you guys remember that from the previous math class? We had negative exponents. Maybe not negative rational exponents. I think we probably did in Math 100. I've taught that for a little while. But we definitely had negative exponents. And so let's do some of those before I look at the rule up here. Let's see, a couple different ways to show this. But let's just start out with what is x to the negative second power? And if we remember, that rule is that's 1 over x to the second. Okay, I've got another way. I don't know if I want to go into this detail. It helps us understand negative exponents. Once again, it's something really at this level of the class, you have to start, I'm starting to mess this up. You have to start memorizing some of this stuff because of speed, but it's good to understand why, because that really is the beauty of this stuff. But let me see if I can, I don't know if this is going to work. I'm using my white pen to try to do this because I had text under this. Let's do this. So let's look at a pattern here. So what is 5 squared, 5 cubed, 5 to the first? Okay, what's the pattern? 3, 2, 1, 0, negative 1, negative 2. Okay, so there's definitely a pattern there. 3, 2, 1, 0, negative 1, negative 2. Well, what is 5 to the first? 5 to the first is just 5. What's 5 to the second? 5 times 5, 25. What is 5 to the third? 5 times 5 times 5, 125. But you already know that. But what do you not know? Well, you might not remember, you might not realize that if I want to go from this step down, I'm going from a power of 3 to a power of 2. And what happened there? Well, we took 125 and we divided it. We're going down. We divided it by the base of 5. 125 divided by 5 is 25. What is 25 divided by 5? It is 5. Wow, okay, let's see if this works. What is 5? Oh, that didn't work. What is 5 divided by 5? Well, 5 divided by 5 is 1. And by the way, we have a rule of exponents. It says when you have a base raised to the 0 power, but you can't have a 0 raised to the 0, but any other base raised to the 0 power is always going to be 1. In fact, we have that way down here called rules of exponents. Where was that? There it is right there. A to the 0 power is always going to give us a 1. Of course, a cannot equal 0. You can't have the base 0. You can't have 0 raised to the 0. But any other base, a raised to the 0 power is going to be 1. And I think maybe this little silly thing that I'm doing right here might give some reason for that. Because when you have whatever base this is, like 5 to the first, well, this is going to be that same base. 5 to the first is just going to be 5. And if you're dividing by 5, it's this 0, 5 to the 0, or anything to 0 is always going to be 1. But really what I was trying to get to was negative exponents. And now here we are, negative exponents. Can you continue with the pattern? And I want more space because these are exponents that have fractions, right? So what happened with the steps here? Well, I got to continue with my pattern. The pattern is divide by 5. What's 1 divided by 5? Well, 1 divided by 5, that's just 1 over 5. And by the way, a 5 is the same as 5 to the first. So notice that negative, what the heck? That negative exponent right there, 5 to the negative first is just 1 over 5 to the positive first. And if you continue with this pattern of taking this and dividing it by 5, well, do we really like to divide by fractions? Let's see, 1/5 divided by 5 over 1. How do you divide fractions? Oh, you have to take 1/5, multiply by the reciprocal, which makes a 5 times 5, that's 5 squared in the denominator. So this is just 5 squared, and it is definitely following a pattern here. 5 to the negative second power is the same as 1 over 5 to that positive 2. Okay, so, we end up kind of just making a quick rule by saying x to the negative nth equals 1 over x to the positive nth. Okay, and also after doing a bunch of this stuff, you'll realize that there's also another shortcut to be used. If I had x to the negative nth and the negative was on the bottom and the denominator, it would actually turn out, if we simplified this and then did a division problem, it would actually turn out that this equals to x to the positive nth up top, which we just call it x to the positive nth. So in other words, another way to kind of think about this, and this is maybe not the best for conception, but good for speed, which is important as well. But look at this. If we're going to, we got x to the negative, we have x to the, how come that's not working? We have x to the, doesn't want to work there. That's interesting. Not fun. We have x to the negative nth. If we write that as 1 over x, it would be to the positive nth in the bottom. And also, if we had 1 over x to the negative nth, if we brought it up top, it would be positive nth. And those are nice little shortcuts to use. Another way to kind of show that, to prove it to you, maybe, it's not a perfect proof, but it kind of, well, no, we don't, I didn't, yeah, actually we did learn this stuff before. So what if we had x to the second up top divided by x to the third? You guys remember the quotient rule from before? Yes, you remember it. When you're dividing numbers with exponents and they have the same base, what do you do to the exponent? You subtract. And 2 minus 3 is just x to the negative first. But wait a minute, what was this going to be anyhow? If I go this way, well, if I have 2 to the second if I have x to the second and x to the third, well, I'm going to reduce 2 of those there, I'm going to reduce 2 down there. That's going to leave me with an x in the denominator and a 1 up top, which is, right? X to the negative first is equal to 1 over x to the positive first, right? So you kind of see how this stuff That's one thing that I really love about math is all the rules have to match together and work. You can't just have a rule work with one rule and then you try to match it with the other rule and it kind of falls apart. It all blends together and shows equality and works almost always seamlessly. Every once in a while we have to have an exception or whatever, but we don't like to have exceptions. We like things to be true if we're going to call it a rule and always true. Evaluate the expression. So here we are with this darn negative, and I ate up too much space over there. I would say the very first thing to do with this problem is to deal with the negative. Deal with it. How do you deal with it? Well, write it as 1 over 9, now raised to what? The positive 1/2. That's dealt with the negative because we put it in the denominator. Now what? Well, now deal with that rational exponent. Can I write it as a radical? The base is 9. We can see the denominator, so index is 2. Power is 1, so we don't have to show that. And we know that the square root of 9 is just 3. So this answer is 1/3. Okay, write with a positive exponent. I'm not happy. I thought I gave myself more space on this problem. Maybe I did I guess I have to use this space over here to make this work. So what was the problem? It was 1 over 216 raised. Boy, that needs to be bigger for sure. 1 over 216 raised to the negative 2/3. And so I would encourage you just to do this problem in nice little steps. Now I've got a negative exponent in the denominator. Remember I told you a shortcut when you have a negative in the denominator is to rewrite that same expression up in the numerator, except the exponent is now positive. So using that idea, I can write this expression in the numerator, but now, that doesn't want to write. Let's go. Nope. There we go. It's now in the numerator, and what changed? The negative sign is now positive 2/3. Now let's continue to break this down. I don't know about you, but a exponent of 2/3, I'm not sure what to do. Well, let's remember that we can write this as a radical and just kind of calm down and realize the denominator is 3, so the index is 3. The base is 216, so the radicand is 216. And I have a numerator of 2, so the power is 2. I could either put the 2 there, or if 216, the cube root of 216, simplifies nicely, well then I'd rather square it after we've simplified it. So we need to figure out, can we simplify that? So the question is, 216, does it break down? And I'm just going to help us right now. 216 is the same as 6 to the 3rd power. So now we've got the cube root of 6 to the 3rd power, and in the end, after we simplify that, we're squaring it. Now, the beautiful thing is the power of 3 and the index of 3 are going to inverse or undo each other, if you will, and we're left with 6. Now don't forget that this is now raised to the 2nd power, and we end up getting 6 squared, which is 36. All right, that 36 goes right here. I don't know why I feel like I need to put this in. I guess it's just comforting. Feels like I got something done. Number 15, yay, I've got space to work here. So number 15, I'm zooming in just because of fractions and exponents. The exponents are already small, and then you got to make them fractions, right? So they're hard to write. So now, one of the beautiful things, I don't know if you're going to think it's beautiful or not, but one of the beautiful things of rational exponents is they are exponents. So they have to adhere to and are governed by the rules of exponents, which we have quite a few rules of exponents. There they are right there. All of those rules of exponents will now apply to our rational exponents. Remember when we said, well, look at that. We just talked about that one, and there it is again. But remember when we said, if you're multiplying exponents with the same base, it's called the product rule. And what do you do to those exponents? You add them, and that screws people up sometimes because they see multiplication and then you're adding. But I explained that last video. And here's another one. When you're dividing exponents that have the same base, what do you do to the exponent? You subtract them. Okay. And then we've got all these other rules I'll kind of tackle as they come up. But there's the rules of exponents, and they all will apply to any problem that has exponents in it. So where was I? There I am right there. Well, look at that. We have a base of 4, and it's being multiplied. So we've got 4 raised to the 1/3 times 4 raised to the 5/3. And remember the rule of exponent says, hey, the base is the same. What do you do to the exponent? Well, all you have to do is just add 1/3 plus 5/3. And adding fractions, you got to have a common denominator, and they do. 3 is a common denominator. So 1/3 plus 5/3 is 6/3. And fractions, even though they're rational, even though they're exponents, they still reduce. What does 6/3 reduce down to? 2. Hey, this is looking sweet. 4 to the second power that's just 16. So that problem really turned out pretty nice. And we used rules of exponents. We used rules of exponents to simplify that. And so that's going to happen. That's our theme for the next page or so. Simplify the expression. Well, we just said if you have the same base, what's the base here? 128 and base 128, and you're dividing, use the quotient rule, which just simply says, what do you do to the exponents? You subtract them. 5/4 minus 1/4. And I know 5 minus 1 is 4/4. Oh, wait a minute. 4/4 is just 1. That's 128 to the first power. That's 128. Okay, and probably didn't need that extra step there, but that's okay. So we've got 128. Now we move on to number 17. Now 17, we've got still the quotient rule going on here. And simplify the expression, okay? It's the quotient rule, so we've got 1/4 minus 3/4. Nope, sorry, 3/8. 8 right there. Uh-oh, we don't have common denominators. Well, if I gave you 1/4 minus 3/8, that's an elementary arithmetic problem, right? So, but we need a common denominator of 8. We'll multiply the denominator numerator by 2 to make 2/8, which is the same as 1/4. And 2 minus 3, well, that gives us negative 1/8. So when we do that subtraction, we get negative 1/8. And by the way, in this class, in any other math class from here on out, and even the previous one, we do not like to write final answers with negative exponents. There's a negative exponent. We need to get rid of it. And how do we legally get rid of it? Write it as 1 over x to the positive 1/8. That is an equivalent statement, but now that blue negative went away because we put that whole expression down in the denominator. Signs change. Number 18. Well, whenever we have a power, which was 3/5, raised to another power, the rule or the exponential rule, or rules of exponents, as we say right here. The rule is, where is it illustrated? Here it is right here. It's called product to a power rule. So is that what I had? Oh my gosh, what were we just doing? What was the problem? Yeah, it's a power raised to a power. Okay, so I got to go back to that rule. Lost my train of thought. And the power to power is this one right here, power rule. Jeez. So the power rule, so notice I've got a, so tiny. I've got a to the r raised to the s. So it's r power raised to the s. So it's a power to a power. And what do you see as an operator? I see multiplication. All you have to do is multiply r times s. So let's get back to it. Here we are right there. Got to zoom out so we can see what's going on. We have a power raised to a power. So we just said that just means 64. That means we multiply 3/5 times 5/6. Well, you know when you multiply fractions, you want to reduce common factors. And of course, common fives, let's get rid of those. Not really get rid of them, they just reduce down to a 1. And then we also have common threes. 3 goes in 3 once, 3 goes in 6 twice. And this thing really simplified down pretty nicely. I'm left with 1 times 1 is a 1 in the numerator, and 1 times 2 is a 2 in the denominator. Okay, now we have this rational expression, or this rational exponent, nasty thing, that we simplified down to 64 to the 1/2. Does that ring a bell to anybody that we can simplify it further? We've got a base of 64. What does it look like as a radical? Well, the denominator is 2, so the index is 2, and that thing looks really nice. What's the square root of 64? Well, 8 times 8 is 64, so the square root of 64 is just 8. And that's the answer for number 18. Let's take a look at number 19. This is called, where's this one at? This is the one I accidentally did the highlighter, or used the highlighter on last time. This is the product to a power. Actually, it's a combination of both. But there, so there it is right there. Let me just show you how it works in the actual problem. So what happens is, it's not the distributive property, but it really kind of feels similar to it. But basically what we're saying here, let me say it this way. We're saying everything in the parentheses must be raised to the 3/5 power, right? We've got two things in the parentheses that must be raised to the 3/5 power. What's in the parentheses? Well, the first one right here is a raised to the 5/4 power, and b raised to the 8/3 power. Now we're back to this problem right here, the previous one. We have a power raised to a power. Now you don't need to write this again. You can just multiply it, but I'm just gonna take an extra step to show that this is equivalent to 5/4 times 3/5. And this is equivalent to b raised to the 8/3 times 3/5. We see some nice things that will reduce, like what 5/5 reduces down, which is now going to leave us with a 1 times 3 is 3 in the numerator. 4 times, is that a 4? Yeah, 4 times 1 is 4. Okay, well, how about the next one? Is anything nice reduce here? How about 3 will reduce with 3, leaving us with b raised to the 8/5. Now you might be enticed at this point to now add those exponents because we're multiplying, but the problem here is this base is a and this base is b. So the rule that you might be accidentally trying to use would say if the bases are the same and you're multiplying, then what do you do to the exponent? You add them up, x to the 5th. right? But the bases are not the same. So this is as far as that goes. And we're done. A to the 3/4 times b to the 8/5. Okay? And once again, just to kind of reiterate, why is it that when we multiply exponents of the same base, we actually, in fact, add the exponent? Well, that's a good question. Well, it's because x squared is x times x, and x cubed is x times x times x. And that repeated multiplication of x could be thought of as x to the 5th, right? And so you're just simply adding up how many of those you have. Number 20. And we have more still, right? So number 20, we got this power to a power thing going on, but we got to be really careful because people forget that everything, when I say everything, I mean everything in the parentheses is raised to the 1/2 power. And I've got quite a few things in there. I've got a 49, I've got an a squared, and I got this b. So every factor in the parenthesis must be raised to the 1/2 power. Like I said, often people forget the numbers. But 49 must be raised to the 1/2. And then what about this? This thing is so squished together, but it's a squared must be raised to the half. And finally, b to the nasty negative 5/8, yuck, must be raised to the 1/2 power. Now you might be getting quicker and quicker and realizing that something raised to the 1/2 power is just square root, right? And what's the square root of 49? Well, this is just going to become 7. And when we have a power raised to a power, we are multiplying. You know, we zoom in a little bit. Well, this is 2 over 1 times, what's half of 2? That's just 1, right? So this exponent just becomes 1. Or if you want to multiply it, 2 over 2, which is just 1. That leaves me with h to the 1st power, and I don't need to write a 1st power. So I've got those two taken care of. Now the nastier kind of problem right here because of the fractions. Well, let's first multiply this, right? Because it's a power raised to a power, so therefore I multiply. When let me do a little sub problem over here. Let me just do a little bit of work over here first. When I multiply this, this gives me b raised to the negative 5. 8 times 2 is 16. Okay, so that's what the result of that is. But how do I deal with this negative exponent? Remember, I can deal with that by writing it as 1 over b to the positive 5/16. And that, I need to make that bigger so it doesn't look, so it actually looks like the base. Okay, so that's what that is. It's 1 over, which puts it in the denominator. So my final answer is going to look like, running out of space here, when I multiply all that together, my final answer is a 7a up top, and this b to the 5/16 is down below. And that's the answer. 7 where to go? 7a over b to the 5/16. Got a couple nasty problems here, and then they start getting easier again. But this is about the nastiest one of all. And let's see if we can do it. Now, last strategy, I said everything must be raised to the 1/3 power. Everything in the last one was 1/2. But it does, it's true. I could do the same thing I did last time and say everything must be raised to the 1/3. Eventually, I'm going to have to do that. I could do it right now, or I could do it later. So it's not always obvious which way is faster. But since I have this nasty fraction inside here, and notice that I have some factors with a's, and I have some factors with b's, like those guys. So that would indicate that I could do some reducing. So that's the strategy I'm going to go with. You don't have to, but I'm going to go ahead and see if I could use my quotient rule to reduce these common bases. So let's see, what do I want to do with this? Notice the 27, it's down below, so I need to make sure it stays down there. I'm going to call it 1 over 27. We got to be very careful because let's not forget in the end, I'm going to do this in red. In the end, we do need to raise it to the 1/3 power. So let me just make sure that is going to happen. How much space am I going to need here? Probably could squeeze it in if I go way out here. Okay, so now what's going on? We're doing the quotient rule, which basically says now I've got a raised to the 2/3 minus 1/2. What about the b? I think I'm going to use another color. I've got b raised to the negative 2/3 minus 1. Now, since I'm subtracting fractions, I might as well call that 1. I might as well call it 3 over 3. So I have a common denominator. Oh, man. All right, so let's go ahead and simplify that. I still have 1/27. Let's work this thing on the side here. Of course, this is just, arithmetic. We do have to have a common denominator, which would be 6. 3 times 2, so 2 times 2. So 4/6 is the same as 2/3. And 3/2 is the same as 1/2. So that will, in fact, 4 minus 3 is 1/6. So this is now going to be a to the 1/6. Now this already has the same common denominator. So we have a negative 2 minus 3 is negative 5/3. Okay, don't forget we must raise all factors to the 1/3 power. Now you can write this down, or you can do it in your head, but you can start losing some pieces here. This is 27. I'm going to write all these factors, and I'm going to show that each one of these factors must be raised to this red 1/3. All right. So let's see, how do I want to, I think I better write this up here. Okay. So look at this. This is 1 over 27. So that's clearly in the denominator. So we've got 27, and that, remember, everything must be raised to the 1/3. So we'll do that. 1 raised to the 1/3. That's just going to be the cube root of 1. So that's we don't have to show that. If you want to put a 1 up there, you can. But we are now going to have other things occupying the numerator, so we don't really need to show that 1 up top, because we've got this guy that is clearly up top. It doesn't it's over 1, so it's up top. And we've got a, and we're going to multiply that, right? So when we multiply that, that becomes 1 over 18. And then we take a look at that next factor, and we've got negative 5/3 times 1/3. So it's going to be b raised to the negative 5 over 9ths. Okay, remember, we always make sure that our answer has positive exponents. The other thing we want to do is take a look at that guy. Let's see, let's just kind of highlight their work right here. Right, isn't 27 raised to the 1/3 power really just the cube root of 27, which just equals 3? So now I've got a 3 in that place. I guess I can go like that to show the equality. Also, this is raised to a positive power, 1/18, so I'm fine with that. But this guy right here is problematic because of that negative exponent. And remember, the easiest way to remedy that is to take this whole factor and write it down here, but it must have a positive exponent if you're going to do that, right? Yeah, I touched that. I knew it was going to get worse. I couldn't help it. There, geez, that looks funny too. But anyhow, you see that's the same there. And so now I wrote it in an equivalent way, but I made sure that I didn't have any negative exponents. And so there is the nasty answer that I was looking for right there. A to the 1/18th over 3 times b to the 5/9. Okay, here is the little statement, the WIMP. I shouldn't call it WIMP statement. But when it says assume all variables are positive, it takes the weight of us having to remember that if we're going to simplify variables that have even indices, that we have to use absolute value. Once they say assume all variables are positive, well, now we don't have to worry about that x being negative, and we don't have to worry about absolute values. So they take away that issue, and you can see that they love that. Assume all variables are positive, assume all variables are positive, assume all variables are positive. Okay, so we're not having to worry on these particular problems about that absolute value piece. Now this problem anyhow is odd, so it wouldn't be an issue. Oh, I'm stuttering. So now let's see. This is the cube root. Now it's asking us to use rational exponents. We are asked to take this radical and change it to a rational exponent. So that means, what does that mean? That means take the radicand, and that is now your base. Negative 8, a to the third, b to the 9th, and it's all raised to the, remember the index is your denominator, and the whole thing is raised to the 1/3 power. Okay, so how are we going to tackle this thing here, right? Now we're going to use the rules of exponents, and remember on this one I'm going to go back to using red, because that's kind of like what I said. Everything in the parenthesis must be raised to what? The 1/3 power. Everything is raised to the 1/3 power. Everything is raised to the 1/3 power. Make sure all factors are raised to the 1/3 power. Well, we've got a negative 8 right there. We've got an a to the third. We've got a b to the 9th. Let's just take this guy over here for a second. And remember that a negative 8 can be written as negative 2 to the third. Negative 8 is the same as negative 2 to the third. And this 1/3 power is just the cube root. So the cube root of negative 2, now the power of 3 and 3, index 3 are matching, so the outcome's a negative 2. Okay, and once again, with an odd index, we can have a negative outcome. So this is now going to be a negative 2. And what is a third of 3? Well, if you multiply that, we get 3 over 3, which is just 1, so that's a to the first power. And what is a power to power we're going to multiply? And you can see what's going to happen here is we're going to reduce common factors. 3 goes into 3 once, 3 goes into 9 3 times, leaving us with b to the third power. And there is the answer for number 22, negative 2ab to the third power. Now, still assuming that all variables are positive, that's awesome, don't have to worry about absolute values. But it says use rational exponents. So why don't we convert this into rational exponents. Now, when you don't see a root index, we know that is a 2. So this is, in fact, x to the 1/2 power. Once again, there's my root index. Where did that 1 come from? Well, right there, right? What is the denominator? Is that, it's hard to see that. The way the typesetting is not very clean. But anyways, this guy has a root index of 10. So if we're going to convert that to exponential form or rational exponent, it's going to be 1/10. Now we know when we have a quotient rule and the bases are the same, we can actually use the quotient rule, which says 1/2 minus 1/10. Well, those guys are fractions, and fractions must have common denominators. So let's go ahead and take this guy and work it way over here. And we know 1/2 is the same as 5/10. So we convert that to have the same exact denominator. So 5/10 minus 1/10 is 4/10, which 4/10 reduced down to 2/5. All right, so this x is raised to the, ultimately, to the 2/5 power. And let's see, did I? Yeah, I played around with this, I think. I typed it in MyLab this way because that's the way we typically leave something like this. We do have to make sure that we have positive exponents, but we do. I typed it in this way and it was fine. And I in some cases, I typed it in as a radical. So I typed it in this way and it worked. And I hit similar problem. I tried another one, and I would have, if it was the same problem, it would have typed it in as the 5th root of x to the 2nd, and it also gave me full credit. So it doesn't seem to be picky about that. Next problem, assume that all variables are positive, yay. Use rational exponents. They're telling us, please convert this to rational exponents. This is x, and remember we're kind of still getting this down, times x, rational exponents. Rational numbers are fractions, right? So there's my index of 3, so that's my denominator. My index of 4, so that's my denominator. Of course, the power on these guys are 1, so there's the numerator. When you're multiplying, what do you do to the exponents? You add them. So that is 1/3 plus 1/4. Better get a common denominator, which is 12. Well, let's see. I'm sure you know how to do this. 4 times 3 is 12, so 4 times 1, it gives a numerator 4. And 3 times 4 is 12, and 1 times 3 gives us a numerator of 3. And now we're able to add. So 4 plus 3 gives us 7/12. Trying to make it bigger. So that's x to the 7/12, and that is my final answer. The exponent is positive, so it's all good. What about number 25? Are we almost done with this? Number 25, one more after that, 26. So what I want to do is I want to do this problem in a certain color and kind of do this in layers, right? So we'll do this one in green. There's my index. It says use a rational exponent to simplify. So we need to rewrite this as a rational exponent, okay? So take that index of 6, and that's the denominator, and then take the power, 5, that's the numerator. So that is the green. Okay, that is the green. So I'll do it all in green. Okay, that is the green. Now let's do this part in red. What does the red say? Well, the red says that all things to the first power, so they don't even show it. But we do know that that root index is 2. So the red is 1/2. Okay, so now what? Now we have a power raised to a power, so we must multiply. This gives me x to the 5/12. It's x to the 5/12. Like I said, I also tried the radical form, and MyLab took it just fine. So that was the 12th root of x to the 5th. That would be the preferred answer that most books would say it, but MyLab was nice enough to take both. They are both equal. Number 26, finally. Okay, number 26. I tried to also do some lecture notes here, so this went a little long, I think. use rational exponents to simplify. So this base is 9. The index, so the denominator is 6. Power is 3, so the numerator is 3. And so sometimes this seems, kind of possibly complicated or something, but this is a fraction. This is a fraction, and fractions do reduce as fractions do. And 3/6 is just 1/2. Now it might be a little more obvious. Well, wait a minute. Why don't I just go back? Why don't I just go back to my radical form where the index is 2? And that problem looks very familiar. What's the square root of 9? Well, that's just 3. So, moving around in forms from radical form, which looks like this, and exponential form, which looks like this, right? Moving back and forth between forms, either way, can be very helpful with simplifying these rational exponents or rational exponents or radicals rather. Okay. All right. Well, I hope that helped out, and I hope you have a great day. I will get this posted so you can start looking at which particular problem you had a problem with. I hope you have a great day and take care. Bye.